In this video, we will talk about random numbers in C++. To generate random numbers, the fundamental building blocks that we usually need are uniform random numbers on the interval from 0 to 1. These are there used in algorithms for other distributions. Since 2011, C++ has some distributions with the library random that you can call using this command, include random. We will later use this for uniform random numbers. Let us first see how we can generate random integers. The basic algorithms for pseudo-random numbers in fact generate non-negative integers in the interval from 0 to m-1 for some large number m, such as 2 to the 16 or 32 or 64. These can then be rescaled to the interval from 0 to 1 by dividing by m-1. One of the simplest methods for these random integers is the linear congruential method that was introduced in exercise sheet 8. To use random numbers, we need to set a seed. This is the positive integer that we use to initialize the sequence of random integers. In exercise sheet 8, this was the variable x0. If we choose the same seed, then if the rest of the code is unchanged, then we get the same sequence of random numbers in a deterministic way. That's not very random. This is a good idea if we may want to reproduce the exact results. For example, if we publish a paper. Typically, we set the seed once in the program, and then we repeatedly generate random numbers from that same sequence. To generate random integers, there is a function rand in C and C++ that can be used to generate them. C or C++ standards don't specify which method it should use, but it generally uses the linear congruential method. To use rand, we need the CMath library header, and we use srand to set the seed. In this example here, s is the seed. Its numerical value doesn't have any meaning to us. The random or rand command generates random integers. So here I'm starting with a constant integer s equals 21, and then I call the function srand with argument s, which is 21. That sets the seed. And then inside a for loop from 0 to 20, I have a cout rand and end the line. So this will print out a random number to the screen. And it will do that 20 times. Now, as long as the seed is the same, it should give the same 20 random numbers or pseudo-random numbers every time. The C++ standard does not specify what range of values that rand produces. The range is from 0 to the variable rand max. As in exercise sheet 8, we can divide by the maximum possible value to get approximately uniform random numbers in the interval 0 to 1. So for example, here we do a cout of rand max to see what the maximum random number is, and then we set the seed by using the command srand, and then inside a for loop we simply call the rand command, which gives us a random integer or a pseudo-random integer. We convert that to a double, and then we divide by the rand max variable, also converted to a double, so that we do division in double precision. And this will generate a pseudo-random number in the uniformly sampling the interval from 0 to 1. There are some limitations to using rand. In Visual Studio, rand max is 32,767. This is a small number, as we may want many millions of random numbers, but we only generate 32,768 different values. That includes 0. Also, there are general, more subtle problems with linear congruential methods. For example, they don't properly fill up a multi-dimensional space. So, for example, if you try to calculate probabilities in poker using a Monte Carlo simulation using these numbers, you will not get very accurate results. Also, the rand command is not safe for parallel code because it stores the current value of the sequence as a global variable. So each processor or each core, each parallel core, does not generate independent random numbers. There is a way to generate better random numbers. In fact, there are better algorithms than the linear congruential method. These algorithms are better at filling up a high dimensional space, and all bits are random. One such algorithm is the Mersenne Twister algorithm that has been available in C++ standard library since 2011. To use Mersenne Twister in C++, we need the library file random. Then we declare a variable of type mt19937_64. We supply the seed, which was denoted as S here, when we initialize it. This will initialize a Mersenne Twister that generates integers between 0 and 2 to the 64 minus 1. Now, these are too large for integer, which can only hold values up to 2 to the 31 minus 1. We would need to use, for example, an unsigned long to store them. So let's look at how to use Mersenne Twister in C++. This example shows how to generate random integers using the Mersenne Twister method. The next slide explains this code. So first of all, we include the library random. Then we have our code for the main function, and then we declare a seed. First we declare a constant integer s equals some number, some integer. Let's pick 31 for the seed. And then we use that s as an argument in this command. So first we declare this Mersenne Twister type, and then we use the command mtrand_s, and that sets the seed. And then inside a for loop, we print out on the screen a Mersenne Twister random integer. Okay, so in this slide, s was the seed. That's a non-negative integer. that we use to start the sequence. MT19937_64 is a variable type, just like integer or double. But it's not a simple numerical type. It is an object that internally does the work for generating random numbers. Now, empty_rand is the name we have chosen for a particular variable, and empty_rand followed by open and closing round brackets is a type of syntax that we have met earlier. It is using a variable like a function, and this is an example of a function object which we have discussed earlier in the module. Now, we have discussed how to generate integer random numbers and how to convert those to a uniform interval 0 to 1. In general, we're more interested in uniform random numbers and trying to generate them directly. To use the random library to generate uniform random numbers, we first declare a random number generator as done above. Then we declare an object that specifies the uniform distribution. Then we combine the two to generate uniform random numbers. Internally, this does something like what we did in exercise sheet 8 or with the rand command. In this code here, uniform real distribution double is another type of variable, just like a vector double was. Unif is the name we have chosen for a particular variable of this type. And here U is a uniform random number. So when I say constant double U, that is a double. And to give it a value, I call the unif object and I pass empty_rand as an argument. Here empty_rand is an instance of this object, MT19937_64. So this structure is the same that we have used for other objects before. Now, the code for the Mersenne Twister and for uniform random numbers using the random library is not very pretty. Earlier in the module, we covered object-oriented programming. So we will be able to hide this part of the code and never look at it again. We can't just hide the code inside a function because we generate a sequence of random integers where each one depends on the previous one. So instead of a simple function, we may have to use a recursive function or use vectors, or the most convenient way of doing this in C++ would be to use a function object. Now let's introduce a few concepts on random variables that we're going to need. So let's first discuss continuous random variables. A continuous univariate random variable x is specified by its probability density function, or PDF, that we denote here by f of x. By definition, f of x has to be positive, and it's normalized so that its integral from -infinity to infinity is 1. That means the total probability is 1. This function f is related to the cumulative distribution function, or CDF, which we denote by capital F. And they're related by f of x equals integral from -infinity to x of f of t dt. Now this quantity is essentially the probability or cumulative probability of finding x in the interval from minus infinity to x. So for example, here is an example of a probability density function. It could be a Gaussian or another similar distribution. The total area here has to be 1, so that the total probability is 1. And then let's suppose I want to calculate the probability of finding a random variable between the left tail of the distribution and up to some point x here. Then I would have to calculate the integral that corresponds to this shaded blue area, and that would be the function capital F of x shown here. So I would go from here to here, and that gives this area. And obviously if I calculate the whole area under the curve, I would get 1. So the CDF or cumulative distribution function always has to start from 0, and then in the end it tends to the value 1 once you integrate over the whole curve or under the whole curve. We may also be interested in discrete random variables. A discrete random variable x takes values in some finite or countable set, for example the non-negative integers. We can still define the CDF as for continuous random variables by summing over all possible values of x that are lower or equal to some number. So essentially, instead of having an integral like we had before, now we have a sum over k here. For a discrete random variable, instead of the PDF that we had before, we now have the probability mass function that's denoted by capital P. So that's the probability of x being equal to k. For example, for the Poisson distribution, the probability mass function is given by this formula here. That's the exponential e to the minus me to the k divided by k factorial. And k takes the values 0, 1, 2, and so on. That's non-negative integers. And let's look at the most basic example of a PDF. That's a uniform distribution. Again, now we've gone back to continuous random numbers. So a probability density function f of x for a uniform distribution is equal to 1 for all values of x between 0 and 1. So that's shown here. Obviously the area between 0 and 1 is the area of this square, which is 1 times 1, so that's equal to 1. So this is normalized properly. The total probability is 1. And then if we want to calculate the CDF, we integrate over the function f of x dx from minus infinity to, or actually from 0 to x. So the integral from minus infinity to 0 is 0, and then we continue from 0 to some value x when doing the integral. So in the end, it's only the integral from 0 to up to some value x that counts, and obviously the integral from 0 to x of dx is simply equal to x. So that's the CDF or cumulative distribution function. It's simply capital F of x equals x, with x being from 0 to 1. Once we've generated uniform random numbers, we can use them to generate other random numbers that are distributed in a different way, such as a Gaussian distribution or another distribution. These other distributions can be continuous or discrete. We will cover a few simple methods here. Now, to say that U, capital U, follows the uniform distribution on the interval 0 to 1, we are going to use this notation. U tilde unif and then the interval 0 to 1. So that means U follows the uniform distribution on the interval from 0 to 1. Now let's suppose I want to study the Bernoulli distribution. The Bernoulli distribution with parameter p has a number x which is equal to 1 with probability p and 0 with probability 1 minus p. So that's the Bernoulli distribution. And I want to draw samples from it. I want to generate x that is distributed in this way, described here. So to do that, one way to do it would be to generate a u, a random variable u that's uniformly distributed between 0 and 1, and then set x equals equal to 1 if u is lower or equal to p, or 0 otherwise. So that's if u is greater than p. Now, obviously this works because the probability of u being lower or equal to p is equal to p. As another example, let's look at the binomial distribution. Suppose that y follows the binomial distribution with parameters n and p. Then y has the same probability distribution as the sum of n independent Bernoulli random variables with parameter p. That means we can generate a y that's binomially distributed with parameters n and p by generating independent random variables x1, x2, and so on up to some number xn, where each of those is Bernoulli distributed with parameter p. And then we can set y equal to the sum of all those independent random variables. And we have a sum from 1 up to n. And then we get a number y, which is binomially distributed with parameters n and p. Now, obviously, the drawback here is that we have to generate a large number n of random variables just to get one random variable y that's binomially distributed. For small n, this is okay, but when the number n is large, then there are more efficient methods for doing this.